Okay, I want to continue on with our discussion about frequency response. Now, remember, we're talking about a completely different method of looking at the control system, or a system and then a controller added to it. Uh, in the root locus method, what we were doing is looking at the roots of the characteristic equation and the transfer function, and then from those roots, which tell us the natural frequency of the system, we can um, figure out how the system is going to respond to an input. Okay, so this was one method of looking at it, and we talked about it last time with the idea of, well, what if we had a function, a mathematical expression of a parabola? And what we were doing in the last method was finding the roots, the zero crossing of that, and then predicting the motion of the system from those natural frequencies. Now, in this case, the frequency response, what we're doing is we're looking at the solution and how the system responds to a whole range of frequencies from 0 to infinity. What is the system going to do? And so that's where we get the idea of frequency response, how it responds to a different frequencies. Now, I want to make a couple things clear. We've talked about this a little bit, but I want to reiterate it. One is that we're going to be feeding the system a sinusoidal wave. Okay, now this may seem a little bit weird, but if you remember, our Laplace domain actually is a sinusoidal wave. Because if you think about it, we have these poles in here, and how did we characterize this? This was an omega. An omega is a frequency. A frequency of what? It's a frequency of a sine wave. And so all this time we've actually been talking about frequencies. Okay, that can get a little lost in here, but we have been talking about frequencies. And so we're going to be putting these frequencies into our Laplace transform and the transfer function, and seeing what comes out. I want to remind you of this. When we put a sine wave into our system, and it moves through the system, then we will get a sine wave out. Okay, we'll get a sine wave out in a linear system. We will get a sine wave out of the system. Now, it will not necessarily be the same that we put in. And so let's look at what is the same. This will be the same frequency. Okay, so what we put in will be the same frequency that we get out. Okay, so that will be the same, but the magnitude will change, and the phase will change also. So what we end up getting in here is the amplitude, the absolute value of the G, and here we get the angle of the G. And so we're looking at the absolute value for the magnitude and the angle. Now, we're going to spend some more time looking at this in great detail, but for now, I just want you to think about this a little bit graphically. What we're talking about is a couple of sine waves, one an input sine wave and an output sine wave, and they will differ in magnitude. You can see here and this isn't hard to imagine. Okay, we've got our input here that gives us our amplitude of our input, and then our amplitude of our output in here. Okay, so what we're looking for here is the magnitude ratio. Okay, we want to know the ratio of the the output to the input. Okay, and we're going to do some funky stuff in here with this 20 log to move it to dB. But for right now, I want you to just focus on the idea that we're looking at the ratio of the magnitude. Okay, and so we're going to look at the amplitude of the input wave. We look at the amplitude of the output wave, and we ratio those two, and we're going to call that a magnitude ratio. Okay. Then we've got we've got a time shift in here. We can look at any common point, a peak or a valley or a zero crossing or whatever it is, and we can look at the shift in here, and that shift will tell us about the phase shift of the system. Okay. Now, again, let me reiterate, just so we're all clear on this. In an ideal controller working in a system, these two waves would lay right on top of each other. We would have no change in magnitude, and we would have no change in phase. Okay, what we put in is what we get out. That's the ideal system. That's what we're looking for in here. Okay, so that's where we're going for and what we're looking for, and that will tell us a lot about the performance of our system. Okay, so now the interesting part about this, and where we're going to go next, is actually calculating these guys. Okay, because if we think about this, we're coming in here and we're going to create a magnitude plot for our frequency, and we're going to create a phase plot for our frequency, and we'd like to create a plot that for a whole range of frequencies, and we would like to know what happens over this whole range of frequency. That means that we've got to calculate these guys over and over and over again. Okay, we've got to calculate it at a low frequency and a little bit higher frequency and a little bit higher frequency, higher. And this would be the brute force method of calculating it, is just calculating a bunch of points along here of the magnitude ratio for a variety of frequencies, and then plotting a line through that. It's likewise for the phase. Point for frequency, and we would end up then plotting a line through that, and we could create our magnitude phase plots for that. And so we want to see the mathematics for that, and we're going to explore that. And then once we get the mathematics down, we're going to see if we can then learn how to sketch it and kind of shortcut this a little bit. And so that's where we're headed in the next lecture.